Narcissus was a handsome Greek youth who was cursed to fall in love with his own image in a pool of water. It is said that Narcissus ultimately changed into the flower that bears his name, the narcissus. In those days, people obviously didn't have mirrors. So, Narcissus had never seen himself before he went and looked at himself in a pool of water. Most of us, though, use mirrors for personal grooming every day. However, not many of us know how we are able to see a likeness of ourselves in mirrors. The images that you see on a polished surface can be explained with the phenomenon of the reflection of light. Light from your body and other objects reflects from shiny surfaces, like mirrors, to form an image of those objects on your eye lens. At the end of this lesson, you will be able to define reflection as a property of light, define terms related to reflection, incident ray, reflected ray, and normal, state the laws of reflection, define images, identify the characteristics of images formed by a plane mirror, convex mirror, and concave mirror. Apply the mirror formula and sign convention to find out the relationship between distance of object and image from a mirror. When a ball is thrown at any surface, it bounces back. Similarly, when light rays are incident on a surface, they bounce back. The bouncing back of light rays thus is known as the reflection of light. Based on the nature of the reflecting surface, there are two types of reflections: regular reflection and irregular reflection. Regular reflection is caused by a smooth surface where all the light incident on the surface is reflected in a definite direction. Regular reflection is caused by plane mirrors, still water, and other smooth surfaces. Irregular reflection, also known as diffused reflection, is caused by irregular surface of the objects. The irregularity in the surface makes the incident light bounce back in different directions. Wood, wall, and other such irregular surfaces cause irregular reflection. Let us examine the phenomenon of reflection and the terms related with it. An incident ray is a ray of light incident on an object or a reflecting surface. A reflected ray is a ray of light that bounces back from a reflecting surface. The point of incidence is the point of an object or a reflecting surface at which a light ray is incident. Normal is an imaginary line drawn at the point of incidence, perpendicular to the reflecting surface. The angle of incidence is the angle between the incident ray and the normal, and is denoted by I. The angle of reflection is the angle between the normal and the reflected ray, and is denoted by R. Let us examine the properties of reflected rays by conducting an experiment. To begin, you need to fix a sheet of white paper on a drawing board. Draw a line MM' on it and mark a point O at the center of the line. Draw a normal ON on MM'. Next, draw IO, the incident ray, in such a way that angle IOM is less than 90 degrees. Place a strip of plane mirror vertically on MM'. Then fix two pins P and Q on the incident ray IO. P' and Q', which are the images of P and Q respectively, are observed from the other side of the normal. Two pins P1 and Q1 are fixed such that these two pins and P' and Q' are collinear. Remove the pins and draw a line OR passing through P1 and Q1 to represent the reflected ray. Now, if you measure the angle of incidence ION and the angle of reflection NOR, you will find that angle I is equal to angle R, and P, Q, P1, Q1, N, and O lie in the same plane. In other words, the experiment shows that the angle of incidence I equals the angle of reflection R. The incident ray, the reflected ray, and the normal all lie in the same plane. The property of reflection can be explained using mirrors. The laws of reflection affect our daily lives in many ways. In fact, we verify these laws every time we look into a mirror, which is a surface capable of reflecting sufficient undiffused light to form a likeness of an object placed in front of it. The likeness showed by a mirror is called an image. There are two types of images. Real images are the images that can be caught on screen. For example, the images projected on a screen or images taken using a camera are real images. Virtual images are the images that cannot be caught on a screen. Images formed in a plane mirror are virtual, as they disappear when the object is removed. Mirrors can be broadly classified into plane mirrors, which have flat surfaces, and spherical mirrors, which have curved surfaces. In this lesson, we will look at reflection in plane mirrors. Plane mirrors have flat, smooth surfaces. Plane mirrors are most commonly used for personal grooming, decoration, and architecture. These mirrors are constructed by coating silver on one side so that the other side can reflect smoothly. To see how an image is formed in a plane mirror, let us do an experiment. Consider an object in the shape of the letter P. From a point X on the object, consider a light ray incident on the mirror at point A. According to the law of reflection, the angle of incidence is always equal to the angle of reflection. Observe the angle of the incident ray as it reflects and travels to the eye. From the same point X on the object, another light ray is incident on the mirror at point B, and the reflected ray travels to the eye. The two reflected rays from A and B are divergent. When extended beyond the mirror, these rays meet at X dash. Thus, the image of the point X on the object is formed at X dash. Consider one more point Y on the object. A light ray from Y on the object is incident on the mirror at C, and the reflected ray travels to the eye. Similarly, another ray from Y on the object is incident on the mirror at D, and is reflected to travel to the eye. Like the two rays from A and B, the two reflected rays from C and D are divergent, and when extended beyond the mirror, meet at Y dash. Thus, Y dash is the image of point Y on the object. Similarly, rays from all points on the object are incident on the mirror. All these divergent rays are extended beyond the mirror to form the complete image of the object. You will also notice that the image formed in this case is erect, laterally inverted, of the same size as that of the object, and the distance of the image from the mirror is equal to the distance of the object from the mirror. These are standard characteristics of images of objects formed in plane mirrors. How will you verify whether the distance of the object from the mirror actually equals the distance of the image from the mirror? Consider two rays from a point object O, placed in front of a plane mirror. The ray of light, which incidents normally at point A, is reflected back along the same path. However, the second ray, which incidents at point B, is reflected along BC. This ray obeys the law of reflection such that N is the normal as shown. The reflected rays AO and BC, being divergent when extended beyond the mirror, meet at O dash to form the image. In triangles OAB and O-AB, angles OAB and O-AB are equal to 90 degrees. Also, based on the law of reflection, angle I is equal to angle R. angles on alternate sides of the transversal on two parallel lines are called alternate angles and are always equal. Here, angle I and BOA are alternate angles. Therefore, angle I equals angle BOA. Angles in similar locations with respect to a transversal on two parallel lines are called corresponding angles and are always equal. Here, angle NBC and angle BO-A are corresponding angles. Therefore, angle R is equal to angle BO-A. Therefore, angle BOA is equal to angle BO-A. Using the angle, and side property of equal triangles, we can say that triangles OAB and O-AB are equal. Equal triangles have equal sides. Therefore, OA is equal to AO', which means that the distance of the image from the mirror is equal to the distance of the object from the mirror. Let us switch to another aspect of images in mirrors, the relationship between the mirror and the image size. You may have noticed that not all mirrors enable you to see your full image. You typically need a tall mirror to view your full image when getting ready to go somewhere. This is why most bedrooms sport tall mirrors called full-length mirrors. Clearly, image formation is affected by the size of the mirror. A simple experiment can help you determine how tall a mirror you require to view your full image. Consider a person of height HF standing in front of a mirror on the wall, where H represents the highest point on his head, F the lowest point on his feet, and the I, E, at eye level. The person will be able to see his full image if he can see points A and B. The mirror requires a height where the incident rays HM and FM, after reflection, reach the eye of the person. These will form an image H', F' when produced backwards. In triangle HEH', AM is parallel to HE, and A is the midpoint of HH'. Therefore, M is the midpoint of H'E. Similarly, in triangle FEF', NB is parallel to FE, and B is the midpoint of FF'. Therefore, N is the midpoint of F'E. Now in triangle H'F'E, M is the midpoint of H'E, and N is the midpoint of F'E. Therefore, MN is parallel to and half of H'F'. But H'F' is equal to HF. Therefore, MN is equal to half of HF. Thus, in order to see his full-length image, a person requires a plane mirror that is half his own height. Therefore, to view the complete image of an object, you need a mirror that is at least half the height of the object. Kids sometimes use mirrors as playthings, where they rotate the mirror in the sunlight to make the sun's rays reflect on another person or an object. Suppose a child uses a mirror to direct the sun's rays to a friend standing at a window on the first floor. Now he wants to direct these rays to another friend standing on the road some distance away. If the lines joining the boy to the two friends make an angle of 120 degrees, by what angle should the child rotate the mirror? To solve this problem, let us see what happens to a reflected ray when a mirror is rotated through an angle. Consider a ray of light IO incident on a plane mirror in position M1, M2, such that OR is the reflected ray and ON is the normal. Therefore, based on the laws of reflection, angle RON is equal to angle ION. which is the angle of incidence I. Therefore, angle IOR is equal to twice the angle of incidence. Let the mirror be rotated through an angle theta about point O, so that M1', M2' is the new position of the mirror, and ON' is the new position of the normal. The position of the incident ray remains the same, but the new angle of incidence is angle ION'. Angle ION' equals I plus theta. Let OR' be the reflected ray such that angle N'-OR' is the new angle of reflection. From the figure, you can see that angle IOR' is equal to angle ION' plus angle N'-OR'. Substituting ION' and N'-OR' in terms of I and theta, you get angle IOR' is equal to 2I plus 2 theta. Subtracting equation 1 from equation 2, we get angle IOR' minus angle IOR is equal to 2I plus 2 theta minus 2I. Therefore, angle ROR' is equal to 2 theta. Thus, for a given incident ray, if the plane mirror is rotated through a certain angle, then the reflected ray rotates through twice that angle. Hence, for the given problem, if the child has to direct the rays to a person standing 120 degrees apart, he has to rotate the mirror through an angle that is equal to half of 120 degrees, that is 60 degrees. Have you ever wondered about how images are formed in a kaleidoscope? A kaleidoscope uses 3 mirrors placed at an angle to produce multiple images. When mirrors are placed at an angle, the reflected ray from the first mirror is incident on the second mirror. The second mirror, in turn, reflects it back to mirror 3. Thus, multiple images of the object are formed. The number of images seen in such an arrangement can be calculated using the formula N is equal to 360 divided by theta minus 1. Based on this formula, if the angle between the mirrors, theta, is 90 degrees, then the number of images formed is 3. Experimenting further, if 2 parallel mirrors are placed with their reflecting surfaces facing each other, the mirrors form an infinite number of images between them. This is because the angle between the mirrors placed in this manner is 0. Mirrors can be placed at angles to change the direction of light received by the eye. For example, 2 mirrors placed at specific angles are used to make optical instruments like periscope. Periscope is used in land and sea warfare, submarine navigation, and elsewhere to enable observers to view their surroundings while remaining under cover, behind armor or submerged. A reflecting periscope consists of 2 mirrors to change the direction of light coming from the scene observed. The first mirror deflects the light down through a vertical tube. At the bottom of the tube, another mirror is placed at an angle to reflect the light towards the observer's eye. Most amusement parks have a hall of mirrors, a traditional attraction. Mirrors in these halls are often distorted into different curved, convex or concave shapes to give the participants unusual and confusing reflections of themselves. They may see stretched, shrunken, or even bloated forms of their images. Sometimes the images are startling, and at other times hilariously funny. Thus, the hall of mirrors can use properties of spherical mirrors to create an unusually funny experience for visitors. Of course, that's not the only area where spherical mirrors are used. You may be using spherical mirrors in your everyday life without being aware of it. In this lesson, you will learn about types of spherical mirrors and their uses. At the end of this lesson, you will be able to Describe spherical mirrors. Identify the characteristics of images formed by a convex mirror and concave mirror. And apply the mirror formula and sign convention to find out the relationship between distance of object and image from a mirror. A spherical mirror is made from a part of a hollow sphere of glass. In other words, it is a plain glass bulging inwards or outwards. Spherical mirrors are further classified as convex and concave mirrors. A convex mirror reflects light from its outer spherical surface and has a silver coating on its inner surface. Convex mirrors are usually used as rear-view mirrors in automobiles. A concave mirror reflects light from its inner spherical surface and has a silver coating on its outer surface. Dentists usually use concave mirrors to examine teeth. You need to be familiar with the terminology used in calculations involving spherical mirrors before you get into more detail. Let's start with the center of curvature. Center of curvature, C, is the center of the sphere of which the mirror is a part. Radius of curvature, R, is the radius of the sphere of which the mirror is a part. Pole, P, is the geometric center of the spherical mirror. Aperture is the surface of the mirror used for reflection. Principal axis is the line joining the pole and the center of curvature. Principal focus, F, is a point on the principal axis. This is the point where the rays in the reflected beam, formed from the incident beam parallel to the principal axis, converge. Focal length, F, is the distance of the principal focus from the pole of the mirror. Objects seen in the mirror are closer than they appear. You may have seen this warning sticker on the rear-view mirrors in your cars and bikes. These rear-view mirrors are actually convex mirrors. Rear-view mirrors help the driver to keep an eye on a large area behind the vehicle by providing a wide field of view. The behavior of the light rays reflected from a convex mirror varies based on the angle of incidence on the mirror. Let's take a look at a few cases of reflection of a light ray from a convex mirror, taking the example of a rear-view mirror. In the first case, incident rays are parallel to the principal axis. In this situation, the reflected rays appear to pass through the focus. In a rear-view mirror, incident rays parallel to the principal axis enables the driver to see the car traveling exactly behind his car. In the second case, let us consider incident rays directed towards the center of curvature. Here, the angle of incidence is 0. Hence, the angle of reflection too is 0. Thus, the reflected rays retrace the path of the incident rays and appear to pass through the center of curvature. This enables the driver to see the parking meter on the other side of the road. Next, look at incident rays that are directed towards the principal focus. The reflected rays go parallel to the principal axis. This is how the driver is able to see the traffic signal which the car has crossed. Finally, if incident rays strike the pole at an angle with the principal axis, the reflected rays also make the same angle with the principal axis. This helps the drivers of two cars traveling alongside to look at each other in the rear-view mirror of the car ahead. In concave mirrors, such as a dentist's reflector, the reflection of rays is somewhat different from that in convex mirrors. Concave mirrors help enlarge the images of faraway objects or view objects that you cannot directly see due to their position. As in convex mirrors, reflection of rays in concave mirrors also follows certain rules. If the incident ray is parallel to the principal axis, the reflected ray passes through the focus. If the incident ray passes through the center of curvature, the reflected ray retraces the path of the incident ray. If the incident ray passes through the principal focus, the reflected ray goes parallel to the principal axis. If the incident ray strikes the pole at an angle with the principal axis, the reflected ray also makes the same angle. The focal length of a spherical mirror depends on its radius of curvature. Consider a ray Q parallel to the principal axis incident at point M on the mirror. This incident ray is reflected in accordance with the laws of reflection. When the reflected ray is extended beyond the mirror, it meets the principal axis at point F, which is the principal focus of the mirror. We know that angle I is equal to angle R by the laws of reflection. Angle I is also equal to angle MCF, as they are corresponding angles. Additionally, angle R is equal to angle CMF, as they are vertically opposite angles. Therefore, angle MCF is equal to angle CMF. Therefore, CF is equal to MF. If point M is very close to point P, that is, the linear aperture of the mirrors is very small, then MF is equal to PF. Therefore, CF is equal to PF. Also, PC is equal to PF plus CF, or PC is equal to 2PF, since CF is equal to PF. Therefore, R, the radius of curvature of the spherical mirror, is equal to 2PF. But PF is nothing but the focal length of the mirror. Therefore, R is equal to 2F, or F is equal to R divided by 2. Hence, in case of spherical mirrors, the focal length is half the radius of the curvature. When a beam parallel to the principal axis is incident on a convex mirror, its rays diverge. These rays, when produced backwards, appear to diverge from a point known as the principal focus. The image formed by a convex mirror is always erect, virtual, and diminished in size. The location of the object does not affect the characteristics of the image. Thus, as the object approaches the mirror, the image approaches the mirror too, but not proportionately. This is why the rear view mirrors of cars and bikes are made of convex mirrors. When a beam of rays parallel to the principal axis is incident on the reflecting surface of a concave mirror, its rays all converge at a point on the principal axis. This point is known as the principal focus of concave mirror. Unlike a convex mirror, the nature and size of the image in a concave mirror depends on the relative position of the object from the mirror. Let us examine the characteristics of the image of an object at different points in front of the mirror. When the object is at an infinite distance, the image is formed at the principal focus F. This image is real, inverted, and highly diminished in size. When the object is placed at a finite distance greater than the radius of curvature R, the image is formed between the principal focus F and center of curvature C. This image is real, inverted, and diminished in size. When the object is placed at center of curvature C, the image is formed at the same point, that is, at C. This image is real, inverted, and equal in size to that of the object. When the object is placed between the principal focus F and the center of curvature C, the image is formed beyond the center of curvature C. The image in this case is real, inverted, and magnified. When the object is placed at the principal focus F, the image is formed at infinity. This image is real, inverted, and highly magnified. When the object is placed between the principal focus F and the pole P, the image is formed on the side of the mirror that is opposite to the object. The nature of this image is virtual, erect, and magnified. Now, based on your knowledge of spherical mirrors, let's examine how these mirrors are used in amusement parks. The hall of mirrors that you saw earlier uses combinations of concave and convex mirrors to show funny, distorted images to the viewer. Concave mirrors are converging mirrors. They help us view enlarged images. Therefore, if you stand close to such a mirror, you will see a wider, fatter image of yourself. On the other hand, standing close to a convex mirror would make you appear thinner. With a set of such mirrors around you, you can see a variety of images of yourself, an undoubtedly interesting experience. The analysis of properties of images formed in convex and concave mirrors showed us that these mirrors present images that are either smaller or larger than the relevant objects. The ratio of the height of the image in a spherical mirror to the height of the object is called linear magnification. Linear magnification is denoted by small letter m. You can determine the size of the image reflected in a spherical mirror by using linear magnification. You can also compute magnification as the ratio of image distance to object distance. Thus, the ratio of the height of the image to the height of the object is equal to the ratio of image distance to object distance. Magnification can be unity, greater than 1, or lesser than 1. Magnification is unity when the size of the image is equal to the size of the object. When you look at your image in a plane mirror, it is of the same size as yours. Therefore, the magnification of plane mirror is unity. In other words, there is no magnification. Magnification is greater than 1 when the size of the image is greater than the size of the object. When the object lies between C and F of a concave mirror, the image formed is inverted, real, and bigger in size compared to that of the object. In this case, the image is said to be magnified. Thus, magnification is greater than 1. If the object is placed between F and P of a concave mirror, then the image formed is virtual, erect, and bigger than that of the object. Hence, in this case also, the magnification is greater than 1. Dentists use this situation to view the inner parts of a mouth with more clarity. Magnification is lesser than 1 when the size of the image is lesser than the size of the object. When an object is placed beyond C of a concave mirror, the image formed lies between C and F of the mirror. It is inverted, real, and the size of the image is lesser than that of the object. Thus we say that the image is diminished and its magnification is lesser than 1. In the case of a convex mirror, irrespective of the position of the object, the image formed is virtual, erect, and its size is smaller than that of the object. Hence, in a convex mirror, the image formed is always diminished and its magnification is lesser than 1. Suppose an object is placed in front of a concave mirror. The distance between the object and the mirror is 30 centimeters. The focal length of the mirror is 10 centimeters. How will you find the position of the image? The object distance, image distance, and focal length in a spherical mirror are related. The mirror formula defines the relationship between these aspects. 1 divided by f is equal to 1 divided by u plus 1 divided by v, where focal length f is the distance between the pole P and the principal focus f. Object distance u is the distance of the object from the pole P of the mirror. Image distance v is the distance of the image from the pole P of the mirror. All distances are measured from the pole. The distances measured in the direction of the incident light are taken as positive. The distances measured in the direction opposite to that of the incident light are taken as negative. Try to apply the mirror formula in this problem. According to the problem, u is equal to 30, f is equal to 10. According to the mirror formula, 1 divided by f is equal to 1 divided by u plus 1 divided by v. Substituting the values for f and u in the formula, you get v is equal to minus 15. Take a look at the pencil. It is straight, as we all can see. Now we'll put it into a glass of water. What happened to the pencil? It is bent now. Is the pencil really bent? No, it just appears to be. You can see that when you take the pencil out again. The apparent bending of the pencil is a result of a property called refraction. In this lesson, you will learn about refraction and concepts associated with it. At the end of this lesson, you will be able to define refraction of light, identify the terms related with refraction of light, state the laws of refraction, define refrangibility, define absolute refractive index of a material, state Snell's law and verify it experimentally, define critical angle, define total internal reflection and discuss its applications, and find lateral and vertical shifts in refraction. When a ray of light propagates from one medium to another, for example, from air to water, its velocity changes, and hence, it deviates from its path. This tendency of light to deviate or bend at the point of separation of two media is called refraction. Let's return to our original question. Why does the pencil bend when immersed in water? What happens to it? Actually, the pencil doesn't really change its form at all. The apparent bending of the pencil occurs due to refraction of light as it passes from air to water. The light bends at the surface of separation of the two media. In fact, any object partly immersed in a different medium will appear bent. Let's examine refraction of light as we saw it in the pencil and look at various terms associated with this phenomenon. The ray of light that is incident on a surface is called the incident ray. The ray that deviates at the point of incidence due to a change in the medium is called the refracted ray. The perpendicular line between the two media is called the normal. The angle formed between the refracted ray and the normal at the point of incidence is known as angle of incidence. The angle between the normal and the refracted ray is known as angle of refraction. Let us consider a light ray traveling from air to water. As you can see, the ray of light bends towards the normal. The incident ray and the refracted ray are in the same plane. These observations form the basis of the laws of refraction. The first law of refraction states that when a light ray passes from a rarer medium to a denser medium, it bends towards the normal. When it passes from a denser medium to a rarer medium, it bends away from the normal. As per the second law, the incident ray, the normal at the point of incidence, and the refracted ray all lie in the same plane. The ability of light to bend when passing from one medium to another is called refrangibility. Let's compare two situations where we observe the bending of light. When light passes from air to water, when light passes from air to glass, you can see that light bends or deviates differently in both cases. That is, the angle of refraction in both cases is different. The deviation of light depends upon the nature of the two media and the optical density of the two media. The optical density of medium is determined by a property called refractive index. The ratio of velocity of light in the first medium to that in the second medium is known as the refractive index of the second medium with respect to the first medium. The refractive index remains constant for a given pair of media. Further, the ratio of velocity of light in air or vacuum to that in a medium is called the absolute refractive index, μ, of that medium. If the refractive index of a medium is relatively higher, the velocity of light rays in that medium will be relatively lesser. For example, recall the bending of the pencil in water. As the refractive index of water is more than that of air, light travels at a lesser speed through water as compared to air. Thus, the pencil appears bent. It is difficult to determine the velocity of light in each medium. Therefore, another method of determining refractive index of media was needed. Wilbrord Snellius, a Dutch mathematician, discovered the relationship between the angle of incidence and the angle of refraction for two given optical media. On the basis of this knowledge, he proposed a law to measure the refractive index of a material. This law is known as Snell's law. According to Snell's law, the ratio between the values of the sine of the angle of incidence and the sine of the angle of refraction for two given optical media is a constant quantity. Snell's law can be verified through an experiment using a glass slab, a white paper, and some pins. For this experiment, we put a glass slab ABCD on a white paper and fix this paper on a wooden board. Next, we mark the boundary of the glass slab with a sharp pencil and then remove the slab. Then we mark a point P on side AB and draw a normal NP-N1. In the next step, we fix two pins, P1 and P2, at an angle of 30 degrees to the normal in a vertical position. A minimum of 5 centimeters of distance is kept between the pins to ensure that the points are easily distinguished. Now the glass slab is placed back on the paper the way it was before. On looking through this glass slab from side CD, the pins P1 and P2 appear at positions L1 and L2 due to refraction. Next, we fix two other pins, P3 and P4, where they are in line with the images L1 and L2 of the pins P1 and P2. In the next step, we remove all the pins and draw small circles around them. We join P3 and P4 to meet CD at R. After joining PR, we measure the angle of incidence P1PN and the angle of refraction N1PR. Finally, by finding their sine values and applying it in the formula, we find mu is equal to sine I divided by sine R. If the experiment is repeated using different values of angles of incidence, the refractive index remains the same. Thus, this experiment verifies Snell's law. The principle of Snell's law is valid regardless of the direction of the light. If a ray travels from medium 1 to medium 2 along a certain path, it will follow the same path, while traveling from medium 2 to medium 1. This is known as the principle of reversibility. Now let's consider a case where a light ray passes from a denser medium to a rarer medium and bends away from the normal. If the angle of incidence I in the denser medium is increased, then at a particular angle of incidence, the refracted ray propagates along the boundary of the two media. This angle of incidence is called critical angle of the given denser medium with respect to the given rarer medium and is denoted by dCr. As the refracted ray travels through the surface, it makes an angle of 90 degrees with the normal. Thus, we can say that at the critical angle, the angle of refraction is 90 degrees. If the angle of incidence is more than the critical angle, the refracted ray bends by more than 90 degrees. That is, it gets reflected back into the same denser medium. This phenomenon is known as total internal reflection. This property of light is responsible for an interesting natural phenomenon, mirages in deserts. In deserts, we sometimes see mirages where images of distant trees are visible when the temperatures are high. In nature, images of trees are formed only in water. We may therefore be tricked into believing that we are near water and trees. However, these images vanish as we approach the location. A mirage is caused by the total internal reflection of light. When the sun is high in the sky, the sand gets hot before the layers of air above it. Light rays from trees travel from an optically denser air layer to a rarer layer, and hence bend away from the normal. This bending continues till a stage is reached where the angle of incidence becomes greater than the critical angle, and total internal reflection takes place. The totally reflected rays that reach the eyes appear to come from a point on the ground, where the image of the tree is formed. Thus, we see inverted images of trees even though there is no water around. When a ray is incident on the surface of a transparent medium such as glass, its position changes laterally when it goes out of the medium. This shift of the refracted ray laterally is called a lateral shift. Now let's derive an expression for the lateral shift in a glass slab. Consider refraction of light through the glass slab ABCD shown. Light ray PQ incidence at Q on the face AB of the slab and refracts on passing from air to glass. In the glass, the refracted ray QR incidence at R on the face CD of the slab. At R, the ray again refracts into air and emerges as RS. Thus, RS is the emergent ray. In the absence of the glass slab, the ray PQ would have traversed along the dotted line QU as shown. Since the faces AB and CD of the slab are parallel, the ray RS is parallel to PQ. Hence, in total, the deviation of the light ray is 0, but the ray is shifted laterally. The perpendicular distance between the emergent ray RS and the incident ray PQU is the measure of the lateral shift and is denoted by S. RU represents this lateral shift in the figure. NQT is the normal at Q on the face AB of the slab. QT is the thickness of the slab, represented by T. Angle PQN is the angle of incidence of the light ray in air, represented by I. Angle TQR is the angle of refraction of the ray in the slab, represented by R. Hence, angle RQU represents the angle of deviation of the light ray when refracted into glass. It is equal to I minus R. Now consider the right triangle QRU. In this triangle, sine of I minus R is equal to the ratio of S to QR. Thus, QR is equal to the ratio of S to sine of I minus R. This gives you equation 1. Now consider the right triangle QTR. In this triangle, cosine of R is equal to the ratio of QT to QR, which is equal to the ratio of thickness T of the slab to QR. Thus, QR is equal to the ratio of T to cosine of R. This gives you equation 2. From equations 1 and 2, we get the lateral shift in the slab as S is equal to T multiplied by sine I minus R divided by cos R. Besides lateral shifts, you can observe vertical shifts because of refraction of light. For example, when you look into a swimming pool, you generally feel it looks shallower than it really is. This is caused by a vertical shift in the rays refracted when changing media between air and water. You can verify the phenomenon of vertical shifts through an experiment. Put a coin at the bottom of the trough containing water to a depth h. When viewed from above, the bottom of the trough and the coin appear to be raised. This change in the perceived depth of an object in a denser medium as observed from a rarer medium is known as vertical shift. Refractive index μ of a material is the ratio of real depth h to apparent depth h'. Thus, apparent depth is the ratio of real depth to the refractive index. Vertical shift, denoted as delta H, is equal to the difference of real depth and apparent depth. By substituting the values of h and h', we get the expression of vertical shift as h multiplied by 1 minus 1 divided by μ. The refraction of light through lenses alters the characteristics of images. We can employ this property of lenses in a variety of ways. In this lesson, you will learn about lenses and their uses. At the end of this lesson, you will be able to define a lens, list the types of lenses, analyze the refraction of light rays through a convex lens, analyze the refraction of light rays through a concave lens, apply the lens formula and sign convention to find the image distance, and to find magnification. Spectacles use lenses to form clear and sharp images. A lens is defined as a piece of transparent optical material with one or two curved surfaces to refract light rays. A lens may converge or diverge light rays to form an image. Reading glasses, binoculars, and optical instruments, such as telescopes, use lenses to enhance images of objects. Based on their shapes, lenses can be of 5 types. A biconvex lens is one with a surface that is bulged outwards on both the sides. It is generally referred to as a convex lens. Another type of lens is a biconcave lens that has 2 inward bent surfaces. It is generally referred to as a concave lens. A plano-convex lens has a convex surface on one side and a plane surface on the other. A plano-concave lens is the one that has a concave surface on one side and a plane surface on the other. A concavo-convex lens has a concave surface on one side and a convex surface on the other. Convex and concave lenses are important as they are more commonly used than the other types of lenses. We will focus on these 2 types of lenses in our study. In your study of lenses, both convex and concave, you will use some general terms to identify the location of images. Optic center is a point on the axis of a lens such that any light ray passing through this point emerges without refraction. It is also known as the pole of the lens. As shown in the figure, O is called the optic center of the lens. Principal focus. Principal focus is a point on the axis of a lens. This is the point where a beam of light parallel to the principal axis, after getting refracted, meets in a convex lens or appears to meet when produced backwards in a concave lens. Principal foci occur on both sides of lenses. Principal focus is also known as the focal point. In the figure here, F1 and F2 are the two principal foci. In a convex lens, if an incident ray passes through a focus and its emergent ray passes parallel to the principal axis, then that focus is called the first principal focus. If an incident ray passes parallel to the principal axis and its emergent ray converges at a focus, then that focus is called the second principal focus. In a concave lens, if an incident ray is directed towards a focus and its emergent ray passes parallel to the principal axis, then that focus is called the first principal focus. If an incident ray passes parallel to the principal axis and its emergent ray appears to diverge from a focus, then that focus is called the second principal focus. The distance between the optic center and the focal point is called the focal length. Here the focal length has been represented as OF1 and OF2. A lens in which both the surfaces are convex is known as a convex lens. Light rays incident on a convex lens get converged at its focus. This is why a convex lens is also called a converging lens. Children often use them to make paper burn by making sun rays converge on a point on the paper. Convex lenses are used as magnifying glasses by palmists to study palms. They are also used by fingerprint experts for magnifying and studying fingerprints. Now let's analyze the light rays propagating through a convex lens. When an incident ray is parallel to the principal axis, the emergent ray passes through the focus. When an incident ray passes through the optic center, it propagates without any deviation. When an incident ray passes through the focus of a convex lens, the emergent ray passes parallel to the principal axis. Thus, we can predict the positions and the characteristics of the images formed using convex lenses, based on how a light ray incidents on the lens. For each position of the object, consider two light rays emanating from a point on the object. When an object is placed at infinity, the image is formed at f2 and is real, inverted and highly diminished. When the object is placed beyond 2f1, the image is formed between f2 and 2f2 and is real, inverted and diminished. When the object is placed at 2f1, the image is formed at 2f2 and is real, inverted and of the same size as the object. When the object is placed between 2f1 and f1, the image is formed beyond 2f2 and is real, inverted and magnified. When the object is placed at f1, the image is formed at infinity and is real, inverted and highly magnified. When the object is placed between f1 and O, the image is formed on the same side of the lens as the object. The image is virtual, erect and magnified. A lens in which both the surfaces are concave is known as a concave lens. Light rays incident on a concave lens get diverged away from the principal axis of the lens. An image formed by a concave lens is always diminished due to the divergence of rays. This is why concave lenses are widely used to correct eye defects such as myopia. Thus, a concave lens is also known as a diverging, reducing, negative, myopic or minus lens. Now let's analyze the light rays propagating through a concave lens. When an incident ray is parallel to the principal axis, the emergent ray appears to pass through the focus. When an incident ray passes through the optic center, it propagates without any deviation. When an incident ray is directed towards the focus of a concave lens, the emergent ray passes parallel to its principal axis. Thus, we can predict the positions and the characteristics of images formed using concave lenses, based on how a light ray incidents on the lens. For each position of an object, consider two light rays emanating from a point on the object. When the object is placed at infinity, the image is formed as a point at f1 and is virtual, erect, and highly diminished. When the object is placed beyond 2f1, the image is formed between f1 and O and is virtual, erect, and diminished. When the object is placed between O and f1, the image is formed between f1 and O and is virtual, erect, and diminished. The lens formula defines the relationship between the focal length of the lens f, the distance of the object from the optic center u, and the distance of the image from the optic center v. 1 divided by f is equal to 1 divided by v minus 1 divided by u. To denote the distance and the nature of the image formed by a lens, relative to the object, some conventions have been defined. All the distances are to be measured from the optic center of the lens. The distances measured in the direction of the incident light are taken as positive. The distances measured in the direction opposite to that of the incident light are taken as negative. You can determine the size of the image of an object if you know the magnification of a lens. Magnification, denoted by small letter m, is the ratio of image size to object size. It is also measured as the ratio of image distance to object distance. Thus, magnification is unity when the size of the image is equal to the size of the object. Magnification is greater than 1 when the size of the image is greater than that of the object. Magnification is less than 1 when the size of the image is less than that of the object.